Uranus smells like rotten eggs. That's not a joke. That's peer-reviewed science published in a major journal. And the story of how we figured that out is actually far more interesting than the punchline. In 2018, a team of researchers using the Gemini North Telescope in Hawaii confirmed for the first time that the upper cloud layer of Uranus is composed largely of hydrogen sulfide, the same compound responsible for the smell of rotten eggs, volcanic vents, and sewage. The finding was published in Nature Astronomy, and it settled a debate that had been running in planetary science for decades. Because here's what most people don't realize: we didn't always know this. For years, scientists argued over whether the clouds topping Uranus and Neptune were made of hydrogen sulfide or ammonia. Both compounds exist in the deep atmospheres of gas and ice giants. But which one dominates the upper cloud layer changes everything about how we understand the chemistry and formation of these planets. The reason it took so long to confirm is genuinely fascinating. Hydrogen sulfide absorbs specific wavelengths of infrared light in a very subtle way. Detecting it in the atmosphere of a planet billions of kilometers away required instruments sensitive enough to pick up that signal above the noise of everything else the atmosphere was doing. The Gemini telescope, with its advanced infrared spectrograph, finally had the resolution to do it cleanly. What the detection revealed goes beyond the smell. The fact that hydrogen sulfide dominates the upper atmosphere of Uranus, rather than ammonia, which dominates Jupiter and Saturn, tells us something important about where Uranus formed and how. Jupiter and Saturn formed closer to the Sun, in a region where the chemistry of the early solar nebula favored ammonia compounds. Uranus and Neptune formed much farther out, in colder, more chemically distinct regions of the disk. The sulfur-to-nitrogen ratio baked into their atmospheres is essentially a chemical record of where they were born. So that rotten egg smell isn't just a curiosity. It's a fingerprint. It's the signature of a world that formed in the cold outer edges of the early solar system, under conditions fundamentally different from the gas giants closer to the Sun. Now, what would actually happen if you were somehow standing in Uranus's upper atmosphere breathing this in? The hydrogen sulfide concentration, while detectable, is actually relatively low in the upper cloud layer. The more immediate problem would be the temperature, around -200 degrees Celsius, and the fact that the atmosphere is overwhelmingly hydrogen and helium with virtually no oxygen. You would freeze and suffocate long before the smell became your main concern. The hydrogen sulfide is there, but it's one ingredient in an atmospheric cocktail that is hostile to human life in every possible way simultaneously. Below those hydrogen sulfide clouds, things get stranger. Drop deeper into the atmosphere and pressure builds rapidly. The hydrogen and helium that dominate the upper layers give way to a slushy mixture of water, ammonia, and methane ices under crushing pressure. The region that gives Uranus its classification as an ice giant. Go deeper still and the pressure becomes so extreme that some models suggest methane breaks down into its component atoms, carbon and hydrogen, with the carbon potentially crystallizing under pressure. There are researchers who believe it literally rains diamonds in the deep interiors of Uranus and Neptune. The rotten egg cloud layer sitting at the top of all of this is almost mild by comparison. What makes the 2018 detection particularly significant is what it implies about Neptune. Neptune and Uranus are often treated as a pair. Twin ice giants with similar sizes, similar compositions, and similar positions in the outer solar system. If hydrogen sulfide dominates the upper atmosphere of Uranus, it almost certainly does the same on Neptune. The detection at Uranus gave scientists the framework to look for, and expect, the same signature at Neptune, reinforcing the idea that these two worlds share a common chemical origin story distinct from Jupiter and Saturn. And yet, despite being so similar on paper, Uranus and Neptune are dramatically different in behavior. Neptune radiates far more internal heat than Uranus does. Neptune has violent dynamic storms visible from Earth. Uranus, as we've discussed, appears thermally locked, internally quiet, meteorologically surprising. Two worlds with the same smell, the same basic composition, the same origin region, and completely different personalities. That's the thing about Uranus that keeps pulling planetary scientists back. Every answer generates 3 new questions. The hydrogen sulfide confirms the formation story, but it doesn't explain the missing heat. The missing heat doesn't explain the sideways tilt. The tilt doesn't explain the ghost storms. Each piece of the puzzle reveals that the picture underneath is more complicated than anyone expected. The rotten egg planet at the edge of the solar system turns out to be one of the most scientifically rich objects we've ever ignored.